connector. Alright, I think I got everything in order. So let's get started. It will go well. This is going to be a quite a short stream, everyone. Mainly because it is quite late to start the stream now where I am. And 8 p.m. 8:30 p.m. in the UK. To drop, I will definitely gonna have to drop out early today, just so because so that I can get some sleep and get ready for work tomorrow. You can still see that the stream audio is still scuffed as hell. Well, no, I have no mean to fix it, chat. You just have to handle that. Just have to deal with it. Nonetheless, let me plug this in here. Let's see if this thing gonna change the game in terms of the audio. Well, it is it working? I think it's working, right? Yeah. All right. Ooh, hello. Drop frame coming in. One of these days, I'm gonna have found. I'll find a what it called, like a chat relay on the stream. Assuming I have enough people on chat to even relay any message from. Anyway. Now, oh, you still have a view of my skinny arm in the corner. Let's recap really quick what we done yesterday. So, what we made here yesterday was a updated version of this thing here. And this is a kit that I built for my Voron 3D printer. Now, it looked great with a bit of stringing here, fortunately, but the one thing that I pick out of this is definitely I had used too much filament. This wall of too much material is being used to make up this wall and the base. So what I decided to do in this new version of the CAD is to reduce that by reduce the size of the wall and actually make this giant cutout as well to make room for a servo motor to sit there. Well, however, since yesterday I had a bit of second thought, you may call it, on the the thickness of these wall still, as well as the resistance of this servo motor. Now, So what I'm saying to that is, first and foremost, is it's not the wall on the side here that is I'm gonna be changing today. I'm gonna change the thickness of this 3mm wall and in the center. So originally the idea behind that one was that I can use that. It's meant to mount the fan. It was meant to hold the fan in place. And well, it felt like a good idea at the time. But now I realize if I were to screw in from this side here, and there's a pillar right there. Yeah, hey Dukin, how you doing? Yes, don't get used to a Tuesday stream. I'm literally doing this because I just found a way to stream on Twitch as well, and I go like, oh, I can do that, and here I am, testing it out. Taking it for a spin for a couple hours. Anyway, yeah. So now that I have had this, now this thing exists now. This screw-on bit. So if we put on the view, oh my god, it doesn't show it. Flip it. There we go. Didn't change anything. Ah. Oh, no. Transparency. Oh, it's BT. Sorry, that was the wrong button. Yeah. So now that we screw things on from this side, I realized that this little pillar right there will make up the 3mm needed to hold the thing in place. So I don't need the whole flap to be 3mm anymore. So that thickness there can now can be reduced. So let's do that. Save us some more material. For first, second of all, and this is the thing that I have been doodling on my notebook here, is some thought on how to do this fully mechanical. That's something I kind of want to do, but I know for a fact that it's not the most efficient way to do so. It's more of a cool factor of like a fully mechanical for like flap opener. I may want to make the flap first, huh? Yeah, actually, let me put the note here, make the flap. Yeah, I think I'm gonna call it the flap now on. So let me call that there. So here. So there should be a flap door here that just either direct the air, the air coming out of this blower fan either inward through these triangle here into the chamber, or through this door at the back here, on the side here to the outside. That's the idea. So right now, the defeatist part of me, and honestly the pragmatist in me, is want to use the servo motor to actuate that door. It is the simplest way to do so if you're not if you're fine with playing with electronics, because this is gonna, yeah, it's not that hard. You can, as long as you know how to plug this fan into a GPIO pin on the Raspberry Pi, everything else is gonna work just fine. Nevertheless, I'm still a little partial to mechanical mechanisms, so I will do one final attempt today, just like figure it out how if I can actually make it mechanically toggleable. Got some ideas, sketching down. Honestly, I got more on this, but I filled out more than more page. No, I filled out an entire notebook with those sketches now. You've been struggling with the Pico MMU for several days. I gave up and threw it in the trash. I'm eager to await the new version of MissChanger. Yep. Yeah. Once you get past the single nodal system, the things getting difficult, huh? I'm not, honestly, the more I look at the old version of MissChanger, the V1, the less I am happy with it. Documentation and all. There's like so many things I could have done better back in the day. Mostly internal tolerant, to be honest. But yeah, no, what I'm saying, yeah, no, so things getting complicated quick when we deal with these kind of thing. So the setup guide for MissChanger V1 is 29 pages on top of the 60 something page for the assembly, the mechanical assembly. So things are getting really so the complexity just increase exponentially when it go to tool changer. Not too sure how I felt about that. But yeah, that is one more thing. Maybe that's a good thing for the hardware assembly. I could put everything into a single file instead of having two files, and one of them being pure wall text. Yeah, no. Let's do things one at a time. Let's trim the fan. I don't know why I write it like that, but oh yeah, the funnel wall. Here you go. Set the thing in the middle there. Reduce the funnel wall to 2 mil. So I did everything. I believe I built it rather tough. I think I can just wait. Why is this not giving me anything? Close that. Oh, right now because I built it on top. Oh. 2 mil. Let's just up. Put one down. And that's it. It should reduce everything to 2 millimeter. Nothing else break. Wow, I'm good. I'm good at this. Okay. Wait, did you guys hear that? I think you didn't. I was coughing for a sec. Alright. So I'll just save that. That was an easy save. That was an easy save. So how would we go about making the flappy doodles on this thing? Yeah, make this bigger now. So I reckon about that much is better. Yeah, so I can move this over here and still see the door coming in. Okay, and some dot doodle here. So if you can go look at the top-down view of this system, just notice corner they don't exist, but this is what it looked like there. This is the groove that the flip need to fly in. Right, between that and that, right? So there should be a distance here. To deal with that, actually, yeah, to help with all the thinking, let's just start on the sketch. Let's start making the flap. Let's start making the flap. This can go. This can go as well. Okay, that's the guy running a motorbike outside our door. Don't worry about it. Happen every day. Pretty cool though. So this is the flap part. Flap. And for in it I will need the base. So the base now. Okay. Base. Put it up by 0.2 to make some room. Not in that direction yet. 2. it, draw it, grab that hole, and start making some arches. Okay, create that. Oh, come on. Oh no. Yeah, they have the mode. They have the tension mode first, and then that is the normal mode. So we want that mode though. It's a freestyle mode. Press 3 times, 2 times. I mean, like that. Oh, and I definitely do need that line. And yep. Just cut away so that I can see the line that I just selected. The parallel, and put that down like so. Yep, give that one a dimension as well. Now I'm gonna use the diameter because that's what I know, which is not correct. Did I increase it the last time? I didn't increase it the last time, didn't I? Okay, make it 8. It was 8. Yeah, it was 8, so I wanted 7.4? Yep, put 3, put 3. Yeah, 7.3. That's still right. I make that distance 0.2. And of course, to make sure that this thing is centered, put that there. I think people have been watching for a while probably got bored of me doing just exactly this several times already. But it bear noting, and you can never get your cat correct the first time, or most of the time. So you just have to keep it going until you have to do it again and again until you run out of options. You run into the best option you can. Something is off about this gap here. It's not 7.3, it's 7.7 because it's 8 minus 0.3. Yeah, like that. So that gap is now look a lot closer. So now I look at that and I go, that's not a good gap to have. So we're gonna 0.6. But that gap is now 0.2. Okay. With that, I say, oh, I say we can do. No, can still do that. Okay. Do we have a midpoint here? We don't. How do we get that? I don't want to draw a line across. Oh wait, now what we can do, except that's not the point. The reason what we want to have is this distance here would be 1. So that it can be really, well, let's make it 0.8. You know, we're on the tear to make everything thinner. So just 0.8. So that's our flappy doodles. Just extrude it. Now up to face. Assuming this face now did not get changed. Oh right, this face will get changed, but so so I noticed for the fact this face is gonna get changed when I add more feature onto the base here. So let's not pull the face up, but rather let's hide this for now. I want to know this distance here. And I'm gonna have the length. Nope. Okay, we're doing the normal distance thing. Yeah, 98.8 minus 0.2 is 98.6. Yeah, so let's extrude that exact number and set up the face. That way it doesn't break too easily when we actually do make some changes. Okay, and I immediately regret my decision. The flap, I should have made it such that it touched that wall, because that is more important. So delete. So delete the parallel function there. Do this without breaking it. Oh, there's this one too. So, okay. Okay, give it a distance of 0.2. Yeah, because that face there is what I'm going. No, this is the face relevant to that line there. It's the face I'm gonna lay under the bed, so I don't want nothing to build in that area of the flap. That's why I'm gonna put it in this orientation. So when I build the other item, I can build it into this side here. Close that. Put this one back on. Give this one a different color so I can actually see it. Oh, that's the flapping loose. Yeah. Actually, I'm gonna grab some water first before I continue. Yeah, BIB chat. Okay, I'm back. Let's see, here we go. Let's pull this up. Let's... look at that. So If you imagine this, from the top down, gonna look like this right now, right? With a U-turn and then a flip left. So we add a pin here so that we can pivot around it. That's one. We can add an arm coming out. Yes, no, I need a mechanism to twist this arm, to push it arm in and out. The servo, we can do that very easily because the servo can go both way. The servo can go both way. But for a mechanical mechanism, a purely mechanical mechanism, you will need you'll need to have a source of the pushing. And for this kind of design, I say the most appropriate motor to push thing around is the stepper motor for the Z-axis. The front right actually, so there's three servo motor in a Voron, and the Voron Trident. I reckon if we put the gate here near that door, it will be easy for it to no, if we can somehow link the two link the motion together, this motor at the corner here can actually easily toggle this switch. But the problem with that thing is it travels up and down length of the printer for like 250 mil. And the thing that and this thing here only go back and forth around 10 mil or so. In and out like 10 mil or so. Right? So how the hell are we squaring that hole? Let me draw this extra lines here, just so that we can see this clear. This one is vertical, that's one is well. Right, so this go there. This to go there. What's that? Equal, yeah. And up there. Not out right now, so we can make them exactly where they're supposed to be to make them vertical. Like that. Your point. That angle there is about 80, 79, 70, oh, nearly 90 degrees basically, 79. And we draw a line here. So if we have a pin toggling around, the two extreme will be at the peak of those two lines there. It is vertical, and this line will have the diameter of that. Okay, and it don't set it. Set diameter. We also want to know this distance here. Okay. but not once again, now as a solid one. Rotate around. Finally, this thing here is the arc to which it's gonna travel. This arc doesn't mean much at all because when we have a 4-bar linkage mechanism, it will just sort itself out in terms of how hard it push and pull. And more importantly, it is the two extreme that we are targeting, not the path itself. So it only matters these 2 points here. Nevertheless, I draw the arc just so that we'll know that it's there and what it is, the way that it's traveled. And you can see here, if we put it at 15 millimeter, that this distance there is nearly 20. Now let's go with that for now. Let's go with 20. And that is rather important. So we will look at this thing from the side. So this is the doodle, right? That point is on the. That's the point on the thing itself. We want it to go from there to there. This is 20 millimeter. So what I'm thinking is a sort of like a Scott yoke, or just a wheel with a pin in it. Yeah, spin around, and obviously the two extremes. This will need to be 20 millimeter apart. 20 millimeter apart. That way, so when it reaches one end, it will touch it. Okay, now we turning the wheel though. Are we turning in a single direction, or are we turning it in multiple direction? Think about what the thing is. So so this is the rock that we're pushing in and out. Yeah, this is the paddle the wheel. If we want to spin it this way with some sort of latch, have a handlebar, right? Yeah, with like some sort of pusher that's on. To push it 90 degrees, like that. You need to basically imagine it starting here. No, if it starts here, it will end here. Yeah, that's not too difficult. See? Yeah. Like that. So imagine there is a. This is the path of the thing coming in to push on this whole bar. If it want to make a 90-degree turn like that, it'll catch a like a latch thing. So something like that. At that point, yeah. And it will release itself when this at this point here, where this will be released off this. If this point here touch that one, it'll go there and it just slip out of the way. Right. So let's say it's actually impossible, huh? Okay, so we had a wheel of like a So instead of a circle, so this circle is a circle to which pin rotate around. Can get rid of that. On the circle, we make a series of blades like that. Three-dimensionally, of course, so we don't want to have to worry about the blade cutting on that pin. We can push it on this end here. And up, so we can take that, draw a line upward. Oh. Okay, it's not exactly like that, but we can draw it something like that. Yeah. Let's draw it again. Circle. Give it a line. At this point, you go up, and then diagonally you go there, like that. So this one go in, this one go in, this one go in, and this one go in, like that. So basically, when there's a pin, when the pin or rod or something from here coming down, it will catch on that blade, and that blade will travel all the way into that point there, where the blade is now retract backward into the circle, far more than the pin can actually push it, and basically they're not going to work. And as long as there is a catcher mechanism here of some sort to stop this thing from turning backward, this pin, now that it's here, can go back up, assuming that there's some sort of flexi system once again to avoid this blade, this subsequent blade. It can go back up, and then thus what we'll have then is a one-way spinning system with a toggle one-way spinning system, and you need 2 toggle for every 180 rotation. We don't actually need to be worried about too much about the but obviously we need to know where it is in terms of rotation wise, but that means but that would be easy because there are only 4 positions, there are only 4 steps and for revolution. So we can install a switch on this corner here, I would say, so to detect when the flap is in that position, and when it's in that position, it is 2 steps away from fully closed and 1 step away from fully open. If that makes sense. So with that in mind, I would say, so the next thing then is to figure it out. So I'm reasonably happy with that, I think, unless there is something down here that can cause us to be derailed. Let me do some measurement now. Okay, 20. That's gonna, I think I'm gonna lock that in for now. Yeah, no. Okay. So I want this distance to be 20, but how much in terms of space for the wheel do we have? Because this mechanism here, as you can see my screen, this mechanism, this spinny doodad here require a wheel to be spin around, and that wheel needs some blade attached to it, so it might be more space than we actually have. We can reduce it a little bit because by going closer to the center of this flap, the closer we are to this pivot point, that is that circle there, the the less travel do we need to actually actuate it. But we had there's a there's the point of diminishing return, and say that's so important. How much space to get the work percent? We have 30 something. Okay, about 30 mil. Got 30 mil of space to work with. So assuming that the pin itself, the circle in the center here is 20. That's a circle where the pin is going to rotate around, is 20. And let me do the wing here is 10. Okay. Can we even do that? Okay. Yep. So let's test on that design first. Oh wait, no. Yeah, let's test on that design first. No, there's no point of thinking of how other things involved in this before we know if this even work. And I think no matter what, I'm gonna build that item as a separate piece. From the base body, because genuinely the motorized system here might be the most elegant way to do things. If you're not unless you want to avoid electronics like I am. So let's just hide that away, not get tempted by the easy way that things can go. And I will create another body, because this one, let's say, is the wheel. No, not. Oh my god, I just touched something. We'll call this the turbine. God damn it, I know there's a Vietnamese word for it and I forgot. Very cool Vietnamese word for it. Chong chong. Yeah, chong chong. They call it chong chong. Yeah, call it that. There's a space in between. And for that, I will need. I need the base as a reference. Okay, I have base now. And then I'll build something on this face. Would you believe it? We're already 40 minutes in, 45 minutes in. 2 hours gonna fly by like a flash. I've barely done anything. I won't compromise at the 2-hour mark though. Be a rest. If anything, the fact that I've been doing it right now and stuff defeat the purpose of having a stream in the first place. Okay, so Yeah, that line in the middle, that is just there to encapsulate the line to which. No, what am I saying? I need to grab that line. That line is important. So it's that line. Hold on. Alright, just draw a circle. Make it 20. Make it 20. 20 for the center of the pin. Oh, okay. Make a circle and with a hole in the middle. And that hole is dimensionally is 3 mil. Oh yeah, let's put it over here because that's where the what's it called, the flap is currently is the extreme point on that side, and the distance between these two need to be 10. Yep, like that. Just to, I say the dimension here is 0.8. Yeah, so more possible. So what diameter of this do I have now? Okay. And the position of this thing is not very relevant at the moment. In fact, now that I look at this, we have a lot of space. Do we? Okay, let's just try something before we make that kind of claim. Let's see. Let's draw some random in there. Let's draw some random line there. So that one there is, assuming that if every pivot of that face there. Oh no, we can pivot out further. So I'm just doing this for now. These two symmetrical about that. It's likewise with these two symmetrical, and these two lines should be normal to each other and equal to each other. So I need you to catch it, push it, or something like that. Push it on the side there. Honestly, I don't need that 24.6. It just, or just not. So it's not big of a deal just yet. So more space, more room to work with than I was imagined. I'm gonna lie, I'm surprised. Anyway, let's draw some artists. Oh wait, okay, that might not be the best idea. So you see, because this line interfere up into that volume there, we cannot have that over. Not that Let's mirror this pin. Let's mirror this pin over here to fragment that construction line. Because you can imagine this pin going near this rod, what's it, pusher rod coming down? Oh no, this is not a push rod, this is a path of the push rod coming down. Would that be a bad one though? Well, not for the pin I suppose, not for the pin. But no matter what, this wheel that house the wings need to make room for this rod when it comes down. Oops, so then we need the rod when we hit the circle. Yeah, so for now let's just assume that there's a way to make that rod and make the pusher to avoid that path. Which is over here, maybe a little too. Okay, give it this a dimension here. Give it 1 mil. Yeah, 1 mil, like that. And that way, we can guarantee that it's gonna touch. Just put this here no matter which way. Symmetrical. Okay. I need to build a collapse inward. This is what I'm thinking. When this is being fully extended, that one need to be collapsed inward. Maybe. Oh, right. So let's draw a circle here. Tangent to that, and that is what the whole thing to be able to exist within. That doesn't make sense. No, I'm not making sense. First of all, this wheel does not need to be on that face. It could be at an angle, and as long as it toggle the same pin, it should be fine. What we can do, what I should do, is have this point here to revolve around that just a bit, so that when it hit, so when this thing, when this thing come near this seemingly a wall, seemingly wall, it doesn't. It had a way to collapse back if someone push it from the bottom up. Yeah. Yeah, I think that's enough thinking. And yeah, I'm blapping on too much. I think I should start building that. No. I'm building stuff now because I think we have a winner. I think we have a winner. Okay, I'll just stand up plane. Let's move it in a bit. I want to reserve this wall here. The thickness, I mean. Or maybe 4 or 5 mil. I think that's a 4 mil, right? Yeah, maybe we'll keep it the wall to be 3 mil. No. No? 5 mil at least, because threaded insert. Oh my god, it's all need to highlight it so I can see it at least. We push it in. Oh, I believe no, that's something. No, wrong reduction. 3. 3 is fine. 3 is fine. Right now, make it 4. Make it 4. Make the wall 4. Make the ring 4, and make the pivot point 4. Slightly thicker than the thickness of the pin, which is just an M3 bolt. As for the position of this thing, now this will be intricate because we actually want it to be as low as possible. So because the toggle gonna come down here. If my understanding of a trident is correct, the aluminium extrusion gonna hit that bottom there. So let me draw the line up here now. That should represent the height of the aluminium interaction with this. So make it 20, which is where this is actually far higher up than I thought. Okay, that's good to know. This point, I decided I'm going to do this right now. And actually, I put this in one. No. Actually, a strong circle for this one as well. I don't think that matters too much. No, we can always just have hit the wall and just curve around. So as long as that point can collapse into that and down there, should be good. Wait, it's not updated. What's that? That's it. Yeah, just make sure that the sketch is updated to where it's supposed to be. Yep, right there. Oh, wait. This they need to go deeper actually. Yeah, because remember when I say it make everything 4mm? Well, this ring that we are drawing need to be actually 4mm in more, because we need to make a 4mm thing for the what's it called? The wings of them. Control this really quick. I gotta think about it. I don't need. I was thinking about like making a lever arm here and have it toggle down, up and down to get this wheel turning. Now that I look at this, I go like, wait, I can just attach something to the other side, to the aluminum extrusion that held the bed up, and basically add like a pin, something like that on the aluminum arm. Yeah, and it just drop down along with the gantry instead of me figuring out where the pin need to be. Yeah, actually, not a bad idea, I would say. I mean, how many times do we going to what, send the bed all the way to the max position? Right. So, and even if we do, I would say turning off the fan during that time would be a good idea. Won't be too much of a problem if we turn off the fan at the top, the fan at that point. Horizontal. And this will also justify for me just leaving this whole groove open, so that yeah, we'll have more space for the thing to go down with. Okay, I got it. What's this? Why are you? What's this? We don't want it to swing outward, do we? And as much as I am not to, it's not a fast and loose. It's not a strict requirement, but I'd rather this do not access this space. Oop. T tension, sorry. T for tension. And since we are added with this, make that one tangent as well. Make it, oh, I'll restrict everything in the middle. Okay. And these two equal, so that we can lock the lid. Yeah, I'm happy with that. Full constraint? No, no, no. There's something. Oh, there's this one. Yeah, this one can be whatever. I say you get to be a cool 50 millimeter. What's that? Extrude that. Oh wait, no. Now that I have made the choice with this, I probably want to start locking things in. 2.5, 2.9. Oh, not 29. 2.9. The other way, go 4 mil. Yep. So. Save that. Draw same face again. This time we draw the facility. This time we go. Oh no, actually we can still make some more sketch here. So where do we want to pivot this pin around? This needs to pivot inward so that it. Oh no, that needs just slightly inward. Okay. Just realize if we turn it so like this point is where the turning of the door gonna happen. This point is 30 millimeter off the bed. That means we will lose 31 millimeter of print space if we do not want to touch this at all. Hmm. $31mm Z loss is a hefty number. Say that much. So what if we move this, instead of putting this in the center here, the 10 mil, I will put this all the way down, as down as possible. So this now riding on the bottom edge of the. Okay. We got 25. Still quite a hefty loss. What are we doing about this? I just wrote on the documentation saying that we shouldn't access the last 25mm of the build volume in the ZR direction. That's not a bad choice. What else was those? There's had to be a way to toggle it in and out. I mean, there is a way. The pin that's gonna hit that latch is pin that's gonna hit that latch is on the Z exit. Is there a way we can adjust it before at the beginning and then only let it go down afterward? As in, obviously, if the Z, it will this pin, that the pin that's gonna hit that, it's gonna be screwed into the Z asset via a what is it called, T-nut, right? A spring-led T-nut. So if you guys know about spring-led T-nut, I can just loosen it and move it left and right by hand. So moving it left and right is an easy part, but I wonder if there's like a way we can do this via the printer instead of do it by hand. Unless we found a way to pivot this circle out of this way. I don't think so. Not on this side. But on this side, basically this assembly is pointing toward the front. The only thing that acting around, moving around during there where we can capture a motion is the right hand side Z motor. We need a way to disable the selection tool. The top, no, the spinning mechanism. I don't like the idea of anything. No, the key problem is that I don't want to. I want it all to be all automated. That's the key. Obviously, once again, the most simplistic way to do so with a servo motor. I'm just since this is a two-stage stream, which is not normal, I just reckon I just want to use this time to over-engineer this and sing our way around it purely mechanical, so that I don't have to go and run another wire around my printer. You can use the X and Y exit. You can use the exit. We can use the axis. To do so. Then we need a printout on the tester. Done. So I'm thinking, so if we are looking at the email. Careful of the and I'm not gonna work with it 2.4, that for sure. Oh. Turn on the lights so that we need to see. Oh, actually, I can use the Bluetooth headphone for this. Hopefully you guys can actually hear me. Turn this really quick. Oh, I put the precat window back on. So I'm thinking if we had some sort of mechanism up here, so where we can depress, then engage and disengage this wheel from the toggling mechanism, right? And that, the thing that gonna hit that for sure, most likely. Alright, I just walked to the Bluetooth mic, so I hope everyone can hear me. So the thing that most likely that we can use to hit that depression, to depress whatever that mechanism, that toggle down, is this thing here. It's the bottom bit of the X gantry here. So go to that position, for example, and it that would depress something down on the corner, push something down, and that something will engage the mechanism to allow the fan to be toggled. But several problems arise when we think about that kind of thinking. The first one would be, what if, well, the printer just happened to travel to that position in the y-axis and simultaneously in the right position of the z-axis. I mean, if we were to turn this assembly all the way on the other side, like if we point it toward the back, okay, this gap gonna be within the area of the Y travel where the two head is not above the bed. Okay, so if you guys notice on your Voron, especially if you build it right, and especially if you build stock and you build it right, when the gantry is homed in the homed position 0, 0 on the X and Y, the nozzle actually is not above the bed itself. So that's the stock Voron experience. And we can make use of that because that position means there is nothing to be there's no anything to be worried about in terms of loss of Z or Y, because in a normal print we will never get out of the area of a bed. The downside there, however, is now that we've done so, we now move away from the Z. which is the Z motor at the front, is what's supposed to be triggered this mechanism, and now we just turn it 180 around. So now we need to figure out another way to trigger this mechanism. What to do? So it can come down with Z. Unless we want to do some wire. Unless we want to deal with wire and string running on the outside. Yeah, so if we want some strings running on this side here, or maybe running on this side here, to pull the toggle, pull and turn the wheel, we can do that. It's not gonna look great, does it? But we can do that. So just imagine this on this side, really. Yeah, just imagine it on this side, and everything else. Yeah, just imagine everything got mirrored, and the wheel is now on this side. So the motor, that toggle, gonna toggle the wheel is on this side now. So we need some sort of link motor, or the bar, on up and down is to that one. Would not be too difficult, I don't think. It's down here, in fact, it's down here. So I reckon we just have one of those, what? It's like, if you guys know the mechanism in a bin, right? Where there's a pivot here with an L clip, and a pivot here with an L clip. So those are connected via a metal wire, and because the metal wire is in tension, we didn't have to be worried about snapping. So maybe we can do something like that. The downside, of course, is running a metal wire along the sides of your assembly. It's not a metal wire, even maybe even a filament strand, right? A strand of filament, and of course you're gonna need to deal with the trouble of ratio. How much trouble are we talking? How much trouble? Actually, yeah, this is it. Is this the distance need to travel? No, it's not. Okay. This distance here is the distance that all I actually need to travel. That still need to travel. So reference that. Okay, so 21 because I need to go downward by 21 millimeter. So roughly the thickness of 2020. So if we have a L clip, actually this is the time for pen and paper. So let's grab the camera, and if I can find my stands, that's it. So if we look at the 2020 profile, I have my 2020. right? So the length of travel is roughly about that much. Okay. So if there is a pin poking out right there, poking out right there, so if I just take a bolt and I just screw it into a T-nut on the 2020 there, and then have this down here, so we need to travel a bit more than that. So if we did, right, that's about 10, 20, and we push this back. Oh, right, we can do the angle thing. So if we have a 20 circle there, what I'm just talking about. Yeah. Alright, so there's a way a bin work is to have, if you see this, the little kick portion of the bin there at the bottom, usually a little clip here connected to a metal wire. That metal wire go down there to another mechanism, something like that, and that connected to another metal wire that push the lid up. So that lid is pivot about that point, and that is the pivot point there. Obviously, you did not have to stomp as far as the tip of the lid opening, and that is because all this pivoting motion is rely on angular. The thing that will be reserved here is not the distance that travel. This distance of travel is the angle of travel. So that angle there, so we can leverage the same to what we are doing. We can leverage the same idea to what we are doing, because the 2020 is like that, right? So the pins like that as well. So we can create, so depending on how long this pin actually is, there's a circle, this arc, create the arc of travel here. Yeah, the arc of travel. So I think that kickstand is going to be something like that. It's a pin which is going to rotate around. So there's going to be a little, maybe a little thing over here. Yeah, actually I'm just going to do this right there. Yeah, doesn't matter. I'll make it longer than. You want to make it longer? Maybe not. Yeah, it's some length here. Put it there. So when this go all the way down, this go there, flat basically, and that will go that as well. And the angle of motion there, I will translate it to something at the back, and that's gonna allow the system to be toggled. Now we're doing that. I have a feeling that we are going to over-engineer on this. Oh, this is fine, but if we can get away with it, to put a servo and then press a button. Yeah, that was the conclusion I got with this. So, alright, anyway, just finish this thought, and then we're not gonna continue this. It's ridiculous. There's so many extra items and steps to assembly just to have a mechanical latch, fully mechanical latch. And ultimately, what's gonna happen is, what ultimately the fact is, a mechanical latch requires mechanical action. to motions as to capture mechanical motion somewhere in the system to try to move the flipper, the flapper, and that are most likely gonna come from the motion system, i.e. either the XYZ motion of the printer, and it may cause interference, and it may need to whatever I save in the not having to run the 3-wire that for the servo motor may end up translated into may just get converted into firmware trickery to trying to avoid that specific point in space where the system was being utilized. So the complexity of the firmware trickery is maybe just counteract the simplicity of a fully mechanical. Is I think the conclusion I have there. You know what? Yeah. That's my reasoning for not pursuing this little side project a little longer. Yeah, and that's going to be my reason for not pursuing this fully mechanical actually any longer. Oh hey, we got a comment on Twitch. It turned out to be a bot though. How do I ban this bot? Hello? I can't ban him. Wait, how do I? I'll do it via my little console here. They got nuked in Twitch already, so I didn't need to do anything. It's all right. All right. Anyway. So conclusion. Yep, it's a very short stream as it should be. I'm not going to stream on a Tuesday very often, if ever at all. The reason why we're here today is literally because I figured out how to stream on Twitch and YouTube simultaneously, and I was just like, hey, I want to try that. So that's literally all the reason why I'm here. To couple with that, what we have done today is that we went through a little of a side quest, trying to have a purely mechanical system to toggle the to toggle the flapper here on the active chamber temperature management system instead of this servo that attached to the top of this base here. And I think I reached the same conclusion and I did when I first started trying to do this last week, and that is ultimately the servo is better. The servo just better. So yeah, whatever you save in terms of the coolness factor of the purely mechanical system, you're going to pay for it in the trickery in the firmware side. And so we'll get back to this on Friday. Dukin, I don't know if you're still there or not, but yep, thank you for joining us, joining me like always. I don't think there's much about us, I think just you and me. Well, two people is us, right? Anyway, thank you for joining. Thank you for the lots of support. And yeah, I'll see you on Friday. Trying to turn off the camera here. Give me a sec. All right, there we go. There we go. Mute.